Okay, so I've just given a few examples of particle-laden turbulent flows just to give you an idea why we should be studying these problems. So there are some obvious questions that we need to ask about all of these situations. One is like, how long will the dust storm or something last? What is the range, like how far will it spread if it's pollution and things like that? And what is its capacity for damage? There are lots and lots of very obvious questions that you may want to ask. You may also want to ask about erosion and deposition, how landforms come up like dunes and other rock formations. And we will be talking primarily about clustering in this context. Okay, so what is turbulence laden with particles? We're going to be focusing on vorticity, which is just the curl of the velocity vector. And if you could see turbulence, you would see this is a simulation from Johns Hopkins database. You'll see these long stringy objects which are vortices. So basically think of vortices as long noodles, and there are particles whose size have exaggerated a lot, which are living in this turbulent flow. So this is the situation we're talking about. And so if I zoom into a teeny tiny part of a cloud, this is what I'll see in terms of vorticity. So the thing to remember is that these things are very, very hard to compute. That's the case I'm going to make first. So in a cloud, for example, in 1 meter cube, which is about this much, there is 1 billion little droplets. So I'm going to talk about droplets and particles in the same breath. So there's 1 billion of them. So that makes it already very, very hard to compute. And in clouds, we have many, many questions. For example, which cloud will rain? Okay, so we're going to be talking about flows where the Reynolds number, namely the inertial forces divided by viscous forces, this is kinematic viscosity, typical velocity, typical length scale, is way, way, way bigger than 1. This is the kind of flow we're talking about, and these flows are described by the Navier-Stokes equation and incompressibility. Here is like buoyancy, which comes out of temperature, salinity, and other things, but here is forcing by the particles. And in this talk, for the most part, we will pretend that the particles are too small to affect the fluid. So we will set that to 0. That's already one big assumption we're making. So we're going to be making a lot of big assumptions in order to solve something. So now in a cloud, you'll get this idea that, there's like something like 13 orders of magnitude of length scale. The particles could be as small as 1 micron. And so like it's already, and then there's a lot of physics going on. This is just one example for a cloud, but you could have similar examples in snow avalanches or even, coughing, things like that. So we see that this is a complicated problem. That's the purpose of this slide. What? It came? Oh, great. Okay, so the feature of turbulence that we need to talk about is intermittency. And we need not discuss intermittency in any great detail. We will just discuss what is relevant for our particulate flows. So what it says is the following. So this omega is something like a square of a frequency scale, like the vorticity scale squared, something like that. And normally in a turbulent flow, you would say that it goes all the way from some long big time scale to Kolmogorov scale. So like typically this would be, you'd think of it as the smallest scale being turbulent scale. But here is a simulation. Here is a bunch of simulations at different Reynolds numbers by these people. It tells you the following. So suppose your smallest time scale was Kolmogorov scale. Everything would end at 1. But everything is going all the way till 10,000. Of course, the probability of these strong vortices, we can think of them as very strong vortices at very, very tiny scale, and they're way, way, way stronger than Kolmogorov. So, and they're way smaller also, then they can be smaller also than Kolmogorov. The probability of those is small, but as the Reynolds number increases, you see that the probability increases. So this is the feature of intermittency that we want to use, because particles, the teeny tiny particles, so imagine in a cloud, like Kolmogorov scale is 0.5 millimeter, and these particles are 10 micron. So they are very, very, very small compared to Kolmogorov scale. And they respond most to strong vortices at small scale. So just because we know the answer at one particular Reynolds number doesn't mean we know the answer at other Reynolds numbers. So like intermittency works in such a way that right now we are not able to extrapolate. Secondly, like clouds are not homogeneous isotropic, blah, blah. There's lots of other things. But the basic point is that we can't solve this problem by solving it on a small scale. Okay, so this is just a picture visualization of what I said in the previous slide. So this is 500 times stronger than Kolmogorov, of course, square root of 500 times smaller than Kolmogorov, and this is about 100 Kolmogorov length scales. You see that there's a large number of vortices which are very small and very powerful, and even 4,000, there's quite a few. So this is the same point as I made in the previous slide. Okay, so ideally what you'd need is to take the whole cloud, make grids way smaller than Kolmogorov or whatever, solve them, then take each particle, make a grid around the particle, solve for that, match this. Forget it, nobody can do this. So the world record for Navier-Stokes alone, like no cloud, nothing, is this many grids on one side. And that can maximum do 16 meters of a cloud. And the world record for particles is like around 10 to the 5, maybe 10 to the 6 particles, which is about the number of particles in this much of a cloud. So you can't extrapolate and you can't do it. So you have to think of simpler ways to do it. I'm not mastering this. Okay, so we're talking Reynolds much bigger than 1. Reynolds of the particle, where Q is the particle velocity V minus the fluid velocity U. The relative velocity between fluid and particle is very small. Particles are going at almost the same velocity as the fluid. Their size A is very, very small, and this is kinematic viscosity. So we're going to live in the limit where particle Reynolds number is very small and flow Reynolds number is very large. This is not a very good approximation for many situations, but right now this is what we can do, so we'll pretend it's okay. One little spherical particle of radius A, where A is way, way, way smaller than any length scale in the flow, is described, its dynamics is described by the Gatignol-Maxey-Riley equation, which is basically the unsteady Stokes equation. So take Navier-Stokes, throw away the nonlinear term, and this is what you get. So this is the expression for one teeny tiny sphere and its dynamics in the flow. So Q is the relative velocity and X is its position. So if it's infinitely dense, then this R goes to 0. If it's neutrally buoyant, it goes to 1. So R is a kind of non-dimensional number representing density ratio, and ST is the Stokes number. Stokes number is basically the time scale of the particle divided by the typical time scale in the flow. So you can see that for each particle, it remembers its history, and it's a very, very complicated thing to follow, to calculate. We can do the Bassett history. Thanks to my colleague Vishal Vasan, we have a very good way of computing the Bassett-Boussinesq history force, which is explained in these papers. So we are going to be able to solve for a few particles in one-way coupling. They don't affect the flow, flow affects them, and you can solve for their dynamics and ask about clustering. The main question we are asking is clustering. Okay, so what do I mean by clustering? If the particles are homogeneously distributed, they will look like this. If they're clustered, there'll be regions where del dot V. Now I'm pretending that I'm writing a field equation for the particles. I'm saying that particles are described by a field V, not a individual velocity V of each particle. And in these clustered regions, you will get the divergence to be negative. So del dot V is less than 0. And in these empty regions, the del dot V is greater than 0. So particles are leaving from these regions and clustering into these regions. And this is what happens in turbulence. This is a movie by Jason. I think Jason is somewhere at the back. Yeah, so particles effectively leave vertical regions in the turbulence and they go to regions of strain. So this is what happens to particles. They cluster into regions of strain. And we want to ask, is that all that happens? And is there something more interesting in this that's going on? A caustics event is one where two particles are actually dashing against each other. So we talked about a negative divergence region where particles are clustering. Now we're going to talk about something like extreme clustering where particles are dashing against each other. In this place, you cannot describe it by a field equation because at one place and one time you have two velocities. So, yes. Three variables and two equations? Yes, yes. Yes, so for the u, you solve the Navier-Stokes. For the v, you solve the v equation. And for the x, you integrate the v equation. Yeah. Okay, so we're talking about these places and we're going to talk, and field description breaks down in these situations. We call them caustics events. And we're looking for extreme clustering where the divergence not only is negative, but it's like minus infinity. So like it just all goes into one point or to something of smaller dimension than the basic flow. So these things are, why are they important? Oops, what am I doing? Yeah, these things are important, for example, for planet formation where things need to come together to cluster. This is a problem that Vishnu is working on, and with me and my colleague Pallavi Bhatt. I'm not going to, we don't have any results yet to tell you about it, but it's an interesting question we're asking. In marine snow, it's very important. So marine snow is, you know, this slow raining of carbonaceous matter coming from plankton and other living things into the ocean. And this is extremely important for people like us who pollute the atmosphere with carbon dioxide, because 1/3 of all the carbon dioxide is actually grabbed by these living things and taken to the deep ocean. So they help in mitigating climate change effects. We also have to worry about microorganisms which, you know, they need to dash against each other or come and cluster in order to communicate or reproduce. We need to worry about droplets, which by any normal calculation will not give you rain in the cloud. How do droplets collide enough and coalesce enough to give you rain? And the question in all of these is, can turbulence give you unexpected and interesting clustering? So this is the question. We've seen already in the movie of Jason that you do get clustering in turbulence, but can we understand it? Can we break it down? Can we say something quantitative about it? And in order to do that, we are going to take up a toy model. And the toy model is worked on by Saumav and Divya. He's a final year PhD student. She's just finished her PhD and submitted her thesis. She'll be going to Harvard for a postdoc. And so these are two vortices. So the toyest model we can think of is, instead of one vortex, we're going to live in 2D and just take two vortices. We saw that turbulence is just a bunch of these vortices. So right now, can we understand clustering near two vortices? This is the question. Now, if there are two identical vortices and you leave them there, then by Biot-Savart law, they'll just go round and round. They'll just go round and round, and this is what they're going to do. We're not talking turbulence, we're talking this very, very easy problem. And in this easy problem, we're going to rotate with the vortices. So our vortices are always going to be at the same place because we are in a rotating frame. So in the rotating frame, our vortices are always going to be there. What happens to particles? That's the question we're asking. And if they were passive particles, like tracer particles, if these two vortices are there and you, let's say, start a particle here, this particle will just go round and round there, and all these are trajectories of individual particles. They're all cam tori, and nobody will mix with anybody. Nobody will cluster. Nothing will happen if they're tracer particles. But what if these are inertial particles? They have a small Stokes number, small reluctance to follow the flow. And then what happens? So like these were the two vortices. In this rotating frame, what's going to happen is anybody, any particle of this Stokes number who starts in this colored region, the purple region, they will all go and cluster, extreme clustering into one point. So this is the finding that there is extreme clustering even in this teeny tiny toy model of two vortices. So in turbulence, lots more interesting things can happen, but we haven't gone there yet. So as the Stokes number increases, for heavy particles, the kind of number of particles which cluster goes down. However, if they are finitely dense particles, then they can go, I mean, a lot more of them can cluster up to a big Stokes number. So they can keep clustering into 1 point or something like that. The point is that they all perform extreme clustering. They go from a 2D space to a space which is, in this case, zero-dimensional, just a point, and they could go to a limit cycle or a more and more complicated limit cycle, and they could actually go to a strange attractor. So this is just 3 examples. All particles go to a point, all particles go to a 2 limit cycle, and then they go to a strange attractor. And here is the bifurcation diagram. So as particles become bigger and bigger, they do weirder and weirder things, but they stay near the vortices. So they do this extreme clustering and they stay near the vortices. So this is the nice thing that a toy model can tell us. Yes. Okay, if they're rotating in opposite directions, they'll walk in a straight line. So then particles do very interesting things. They can actually, they can actually form funny manifolds. And yeah, that's a more complicated case. But this is just the babyest case. So yeah, the point is, in turbulence, you have like vortices of all kinds everywhere in 3D. So let's break it down and understand. That's the basic point here. And all of that I showed you was without that horrible Basset-Boussinesq history force, which was an integral force for each particle. And I told you we have a good way of calculating it thanks to Vishal. And we use that way, and then like we see how the bifurcation diagram changes. So this would be the bifurcation diagram for a heavy particle. This would be the bifurcation diagram for a particle which is finitely dense. So we show that many more particles can get trapped if they're finitely dense, etc. And not only that, you get all kinds of weird, absolutely weird bifurcation diagrams. So everything with just 2 vortices and a bunch of very, very easy particles because they're all small Reynolds number and blah, blah. So now you can imagine if the Reynolds number of the particles increases, if their shape changes, if various things happen. So this is some ongoing work in the group. I see Rajeshi sitting somewhere in the end. And so we're trying to write better models where we can understand more and more of these things. And I told you that this is all about spherical particles, but most particles are not spherical, right? So like people normally, whenever they get rid of the spherical assumption, they say, okay, let's do ellipsoids. And ellipsoids, instead of falling down vertically under gravity, will actually drift under gravity in Stokes flow. So this is a knee-jerk reaction, like don't want to do spheres, do ellipsoids. And our moral is, do not do ellipsoids. Ellipsoids are a very special class of particle. Most particles do not behave like drifters in the way ellipsoids do. So we remove just one more symmetry from this ellipsoid. That's the idea of Harshit Joshi, who's a present PhD student in my group. So he said, let's just remove one symmetry. So an ellipsoid has 3 planes of symmetry, right, wherever you cut. Let's make it symmetric in 2 planes, but not in the third. So you can imagine that you take an ellipsoid and you bend it like this, like a cashew nut. And then like he's done this extra thing, but already a cashew nut will be a dibilateral. So in fact, ChatGPT gave us this word, but it forgot it afterwards. So yeah, dibilateral. That's like 2 planes of symmetry. Yeah, so this is the body that we are talking about, just a toy body, but it has 2 planes of symmetry and how things change because of it. And so this thing can flutter without wind, without vortex shedding, without cheating. This is what this body does. So if you want to have some fun, 3D print this body, take like a very viscous fluid like honey or something, just drop it under gravity, nothing else. It will do all of this because it has translation, rotation, coupling. So am I out of time?
No, you still have 4 minutes.
4 minutes, great. So yeah, basically this is doing quasi-periodic motion. And you can show that all dibilaterals will do either this or they'll settle or they'll do something, but very, very few of them will drift. So the moral is, do not imagine that an ellipsoid is a brilliant way of generalizing from a sphere. It's not. Okay, so the last thing I want to talk about is back to cloud flows. So we talked about this intermittency story. We talked about, how more and more strong vortices of small scale exist in turbulence as you increase the Reynolds number. This was normal turbulence, but now we're talking cloud turbulence, and Nikita and others have made simulations about cloud turbulence where we have phase change. So what's happening in a cloud turbulence is that there's temperature which is doing interesting things and phase change which is doing interesting things. So what's happening is the following. Particles are leaving vortices, they're living in the surroundings, and because they are cloud condensation nuclei, phase change is happening preferentially outside vortices. And because phase change is happening outside vortices, latent heat is released outside vortices. And you have a temperature difference between inside the vortex and outside the vortex, which is a buoyancy inhomogeneity. And what do you have when you have temperature change? You have lighter fluid here, denser fluid here. You immediately get baroclinic torque. And you get baroclinic torque at very, very small scales. And instead of this green line, you get something like the black line. So you get more teeny tiny scales because of cloud turbulence. And because you have more powerful vortices, more funny things can happen with particles. And because of that, the propensity to collide and the propensity to have rain could be made more likely. This is just a baby simulation in 3 dimensions. We can't make a big claim about clouds, but yeah, so you can see that in our simulation, the normal turbulence looks like this and cloud turbulence looks like this in vorticity. So here we just switched on the phase change and you see more small scales. So the amount of more small scales depends on many things, but this is basically where it's at. So to conclude, we see that turbulence can create unexpected kinds of clustering, like extreme clustering into low dimensional objects, whereas all normal arguments you'll make will not lead you to extreme clustering, they'll lead you to mild clustering. So like this is one nice thing that we see in the most toy example of a flow, of a turbulent flow. And spheres and ellipsoids are not good. Like if you want to think of real particles, they can do a lot more than all of this stuff is telling you. Cloud turbulence can be different because you get these extra small scales that are generated due to phase change. And we have a long way to go. Like here we've made so many zillions of assumptions. So you release them one by one and you'll see that there are many, many problems to solve on the way. So thanks for your attention.
Thank you very much, Rama. Are there questions?
Yeah, I wanted to ask, many years ago, Deutsch and then Wilkinson and Mehling used to look at clustering because of these paths merging and so. How does, I mean, I'm sure it's not a hydrodynamic thing, but I mean, does it have any value here?
Yeah, I think they were looking at exactly this question.
Oh, I see.
They were looking at exactly this question, but what they were looking at is, just the level of clustering that you just put many particles in homogeneous suspension in a 3D turbulence, run the turbulence and see how it clusters. So we wanted to go a little deeper by seeing exactly what happens due to one vortex, two vortices, etc., etc. So like what is the physics, and is it just random clustering, or do you see patterns in the clustering? Is there some fractal dimension it occupies due to the clustering and stuff like that?
So this, when you drop this asymmetric ellipsoids, you showed that they kind of do this kind of pattern. Isn't that similar to like even this, like you see these seeds, right?
Leaves falling.
Seeds, I mean, there are these
Seeds
seeds with
falling.
sort of asymmetric shape. They go around like a copter. I mean,
Yeah. That's why I gave those three conditions, like there's no wind, there is no vortex shedding, and there is no cheating.
But that's in low Reynolds number, right? Usually those things.
No, they're very high Reynolds number.
Sorry, very high Reynolds
number. And there's vortex shedding.
Okay.
So like what I mean, vortex shedding is like cheating, okay? Like when you have vortex shedding on one side, it's going to go to the other side. But these things, they are dropping in honey. There's no vortex shedding. So it's actually incredible that they're doing this. Whereas like for leaves and things, it's very, very credible that they do that.
Okay, so this one even in like extremely high, it's low Reynolds.
Yeah. Like just imagine putting a leaf in honey. Yeah, a very teeny tiny leaf. So no vortex shedding, that's the main difference.
Yes.
And how deep is your tank? How many loops are you able to?
Oh, this one is a theory.
With a 3D.
So if you need to do an experiment, then it depends so much on the exact shape. And we have a particular parameter which determines the shape, so long as it's a dibilateral. And different ones will have different pitches. So you can actually design a pitch. Typically, they'll have a longish pitch, like, 10 or 20 times the diameter. So you need a jar which is many times the diameter.